This is problem 4-2, and the question is, a ferry boat of mass m1 equals 2.0 times 10 to the 5 kilograms moves towards a docking bumper of mass m2 attached to a shock absorber. Shown below is a speed versus time t graph of the ferry boat from the time it cuts off its engines to the time it first comes to rest after colliding with the bumper. At the instant it hits the bumper, t equals 0 and v equals 3 meters per second. So part A. After colliding inelastically with the bumper, the ferry boat and bumper move together with an initial speed of 2 meters per second. Calculate the mass of the bumper m2. So this is an inelastic collision, which means that linear momentum is conserved. So that means that m1 of the ferry boat times v initial is going to equal the total mass, which is m1 plus m2 from the inelastic collision, times the final speed of both of them together. So we know from the problem that m1 equals 2 times 10 to the 5, and we are also given that vi equals 3 meters per second. Now we also, again, know m1 is the same from last time, m2 is our unknown, and v3 is given in part A as being 2 meters per second. So now we can use algebra to solve for m2, which is our unknown variable. So with a bit of algebra, we see that m2 is equal to 10 to the 5 kilograms. So part 2. After colliding, the ferry boat and bumper move with a speed given by the expression v equals 2e to the negative 4t power. Although the boat never comes precisely to rest, it travels only a finite distance, and that is what we are supposed to be calculating. So this is part B. Now, we want distance and we're given velocity. So we know that the relationship between those two is that x equals the integral of v dt, which we are given. So x equals the integral of 2e to the negative 4t dt. And with a bit of calculus, we know that this equals 1/2 e to the negative 4t plus c, because we are integrating without limits, or defined limits anyway. So we know that we can substitute in this expression to solve for c. So if t equals 0, we also know that x equals 0 because this is the initial state. So solving for that, we know that c equals 1/2. Now, we're looking for the value of x as t goes towards infinity. So now we know that this is now equal to 1/2, right? So if t goes to infinity, this term cancels out and just becomes 0. So x is equal to 1/2 meter. Okay, part C. While the ferry boat was being slowed by water resistance before hitting the bumper, its speed was given by 1/v equals 1/3 plus beta t, where beta is a constant. Find an expression for the retarding force of the water on the boat as a function of speed. Okay, so what we're given is F retarding, which we're going to denote here as Fr, is equal to ma. This is Newton's second law. But we can also use the same expression to say m equals m times dv dt also equals Fr, because a is the derivative of velocity. And we do this change because we want it in our answer in terms of velocity. And also, that's what we're given. So Fr equals mass times the derivative of our velocity expression. Now we're given velocity as a 1/v expression, so we take what we're given, which is 1/3 plus beta t, and take that to the negative 1 power. Now we take the derivative of this whole section, m remains unchanged, and we get negative m beta times 1/3 plus beta t to the negative 2 power. Now we can simplify this expression because we want the f sub r expression as a function of speed. So we know that v equals 1/3 plus beta t to the negative 1 power, where we substituted it here. So this is negative m beta v squared.